Assalamu alaikum wa rahmatullah. We are discussing one-dimensional optimization methods, basically the minimization methods, and among them we had analytic, elimination, the interpolation, as well as direct route methods. So part of the elimination methods, we already discussed three of them: dichotomous search, then interval halving, then Fibonacci method. Today we're going to discuss golden section method, which is a slight modification of our Fibonacci method, basically. So golden section method. So in the Fibonacci method, we have seen that L2 prime was basically Fn minus 2 by Fn L0. And the interval L2 was L0 minus L2 prime. Okay. And this gives us L0 minus Fn minus 2 by Fn L0. So you can take common of the L0. So ultimately it will be Fn minus Fn minus 2. Okay. So and we know that Fn equal to Fn minus 1 plus Fn minus 2. So from that one, we can see that our L2 will be basically L0 Fn minus 1 by Fn. So ultimately it will be L2 will be equal to, now if we apply the limit, if the n is goes to infinity, limit n tends to infinity, then your Fn minus 1 by Fn L0. So what will be the case for this interval of uncertainty if n tends to infinity? So this is what I want to say. So similarly, just next formula can also be, next interval can also be figured out as L3 equal to limit n tends to infinity. The next one, that is Fn n minus 2 by Fn L0, or you can also write here as limit n tends to infinity F n minus 2 by Fn minus 1 into Fn minus 1 by Fn L0. So further it can be written as, so as n tends to infinity, these two ratio will be eventually same. Okay, so this will be eventually same. So we can write that this can be approximated as limit n tends to infinity Fn minus 1 by Fn whole square L0. So basically, as you can see, that the kth interval can also be approximated by this one. So if it is 3, then it is 2. So if it is k, then it should be k minus 1. So ultimately, the interval will be limit, if we give the limit n tends to infinity, f n minus 1 by fn k minus 1 L0. So 3 was here, 2 was here. So similarly, if k is here, it will be k minus 1. Bottom line is, if n is too high, the Fibonacci numbers will approach to infinity. So they will have a constant value. So this is also somehow our golden ratio. So this is the formula we are going to see. And now we want to show that this is actually will be a golden ratio, or a ratio that is rarely available in other cases. So let's see that. So we have our formula of the Fibonacci number, that is Fn equal to Fn minus 1 plus Fn minus 2. So now if you divide both of them by n, the middle one, so basically Fn minus 1 equal to 1 plus Fn minus 2 by Fn minus 1. Okay, so now if we define gamma equal to limit n tends to infinity Fn by Fn minus 1. So if we apply this formula here, so we can write the equation. This equation as gamma, which is equivalent to 1 by gamma plus 1. Okay, so if you simplify that, there will be gamma square minus gamma minus 1 will be equal to 0. Now, if you see that this is, now based on this one, the formula that we have figured out for our iteration, the interval of uncertainty of kth one, which is which was limit n tends to infinity Fn minus 1 by Fn square L0. Sorry, it should be k minus 1 L0. So now what you can see here is that since this is gamma, we can say this is actually 1 by gamma. So including the limit as well. So 1 by gamma to the power k minus 1 L0 is basically our LK. So this ratio is actually known as a golden ratio, and which will be figured out from the solution of this one. Okay. So if we find out the solution of this one, then we can easily figure out the ratio. And if we plug in the value here, this will be 0.618 k minus 1 L0. Okay, so based on a golden ratio, and in some other textbook, you're also going to find that this is a ratio. Say if you have a number R, and if you add 1 with that one, and it will be equal to the inverse of that one. So this is the same principle of your golden ratio. Eventually, if you calculate, then you're going to get the value as 0.618. So this is our the formula related to the golden ratio. Okay, now let's see one example to related to this one. So for the example, what we have to do is we have to take the L2 star. So L2 star will be basically fn minus 2 by fn L0. So it can be written as fn minus n2 by fn minus 1 into fn minus 1 by fn into L0. So ultimately, this will also be, if you apply the limit, also be L0 by lambda square. So this is how we are going to find out the L2. And as you can recall, if this is our A, this is our B, and this will be A plus L2 star will give you X1, and B minus L2 star will give us the X2 value. So based on these two value, X1 and X2, basically we have to find out the function values. And then based on the principle of your unimodal function, we have to eliminate a portion of the interval. So we'll go to the next interval. So this is the relevant theory which is been covered for this one. Now, based on this one, let's see how we can solve one problem. So the same problem we try to solve, and the function given here is basically f x. Even though in the book you are going to see that there are few other example related to your Fibonacci and golden section method, but I will cover the same principle just to show how it's the same, all four methods can be applied to a same problem. So now interval, and I will advise you to solve those problems, those are given in the book. So the interval was 0 and 1, and based on our formula, we can find out our L2 star will be basically uh, will be basically 0.3, and if you apply the values of here, then of your golden ratio, then it will be 0.382 L0. So we apply directly here, 0.382. Now, since we have a fixed ratio, so you are going to see that less calculation will be required in this method. So once you have the value of L2 been known, so our X1 value will be 0 plus, that is A plus, 0 plus 0.382. So 0.382. And our X2 value will be 1 minus 0.382, that is 0.618. So next is find out F1, which is Fx1 will be minus 0.427076. And F2, which is Fx2 will be minus 0.545076. So if we plot it, this is our AB, and this is our X1 and X2. Definitely X2 is higher, X2 is smaller than X1. So F1 is greater than F2. So delete or discard, basically A to X1. So a new interval will be formed. New interval will be from 0.382 to 1. So you can also write equal to your 0 into 0.382. So let's go to the next one. So the next one is interval is given as 0.382 to 0.1. Sorry, 1. And now the two other interval. Already one interval is there in between, which is 0.618, and which is also our x2 value. So next value, x3 value, how to find it out? So x3 value will be basically the new value here, which is in our case x1 plus this one minus this one. So basically, in this case, b minus x2. So 0.382 plus 1 minus 0.618. So this will give us 0.764. Now let's calculate the function value here, and which is f3. Already f2 value is known. So, and your x3 is somewhere here with 0.764. And if you have calculated the value, it will be around minus 0.5623. So as you can see here, this is larger, this is higher than this one. Okay. So make it a bit short. Okay. So we can see that f2 is greater than f3. So we have to discard x1 to your x2. So this is deleted, which is equivalent to your 0.382 to 0.618. So new interval. I'm trying to solve this very quickly, so that is why the handwriting may not be good, just to cover up the syllabus. I'm just making these videos. So if I have time, some later on, I'll try to make it better. But from now on, this is what you have to be happy with. So now, new interval, after discarding that one, will be 0.6182, basically 1. And x4 calculation is similar. So if you plot it, if you draw it, so now new interval will be 0.6182, 1. And already we have 1 point, which is our x3 is 0.764. So x4 will be the first value, that is 0.618, plus the last value, that is 1 minus the middle value, 0.764. So this will give us 0.854. So here, somewhere here is your x4, that is 0.854. So now if you find the value of f4, that is fx4 will be minus 0.5515. Now definitely this is higher than this one. This is smaller than this one, basically in the negative. So this is the notation will be opposite. So f3 is somehow smaller than f4. So we have to delete. We have to delete the 0.85421, that is equivalent to basically x4 to b. So the new interval will be 0.6182 to 0.854. So with that one, plot it again. So 0.618, 0.854. Also we have in the middle, we are not sure which one we have here. Somewhere here we have x3 is still there, 0.764. So formula is same for your x5. First value, that is 0.618, plus your last value, that is 0.5854. 54 minus 0.764. So that will give us 0.708. So as you can see, your x5 is appearing somewhere here. Now calculate the value of x5, which is f5 is minus 0.5607, which is more actually greater than. So f5 is greater than f3. So you have to discard that portion. So f5 is greater, but in magnitude it will be actually smaller. And this is the scenario. So you have to discard this portion. So our final interval or new interval or final interval will be 0.708 to 0.764. So this is your method of golden section. And as you have seen, how many steps you want to go, it actually depends on you. You can go as precise as possible, and maybe those criterion can also be applied. But in the previous methods, we could have figured out the number of n, which can be iteration, or it can be twice n, which can be your number of experiments. So based on the definition, you can actually find out the value. So this is the last of the elimination method. So see you in the next class, inshallah. Assalamu alaikum wa rahmatullah.